Hello and welcome to our first class in Bayesian modeling. This class will talk about what is arguably the most controversial part of Bayesian modeling and Bayesian analysis, which is prior information and prior distributions. In this video, we'll look at two topics. The first is a look at prior information and how prior information is used to create prior distributions. And the second topic looks at a specific approach to this, which is known as conjugate priors. Okay, let's start by reviewing again Bayes' rule as we saw it in the last lecture. And in that case, we were specifically looking at how we obtain the posterior distribution for model parameters, which we designate as theta. And this is a bold theta to indicate that it's possibly a vector, possibly a set of vectors and even matrices. And bold x to indicate it's a matrix of data that we have in our particular problem. Now, for frequentists, they would only use the likelihood function, and this would be all they would use in order to obtain estimates for the parameters for their models. However, a Bayesian uses more than the likelihood function, but also uses prior information, and this is represented in Bayes' theorem or Bayes' rule as the prior distribution in a product with the likelihood function divided by the evidence. And of course, we know that we can use the sum rule or conditioning to break apart the evidence. So this is the basis for doing Bayes' rule and Bayes' analysis. The question, of course, is how do we obtain the prior? And it's the use of prior information that, in fact, is controversial with frequentists because they just want to use the data. But in fact, there's more information available in most problems than the data. And the argument that we make in applying Bayesian inference to problems is that we'd like to use all the information that's available to us in order to solve the problem at hand. Okay, so characteristics of prior information. It's unfortunate, but the choice of the prior and the use and the way in which prior information is converted into a prior distribution doesn't have just one effect. In fact, it depends upon the problem. It depends upon the amount of data we have available to us. So in fact, the effect of the impact of the prior on the problem can be very small and not very significant to very large and extremely important. And it just depends upon the problem we have and the amount of data available to us as to how much of an impact the prior has. So the choice of prior is very important for us. It's also important to note that there's typically a lot more information that's available to us than we can specifically put into a prior distribution. So technically, we'd say that prior information does not precisely determine prior distribution. What we try and get in a prior distribution is an approximation to what we know about the problem that we can use for problem solving. But there may be more information that we just are not able to directly bring to bear on the problem. Okay, common approaches to developing a prior distribution. First of all, the most common and arguably the most accepted is the use of base case or base rates that come from an existing population. So for example, we might know something about the rate of a flu in an existing population of a country, of a state, wherever it might be. We might know about, notice it says existing populations, we might know something about subpopulations. So we might know, for instance, the rate of breast cancer among women over the age of 50, or among women who are African American between 30 and 40. These are things that we would know as base rate or base case information that we would like to use. And this is something that we should always use if it's available to us as a way to develop that prior distribution. Subjective probabilities are another way to go about it. We typically think about this as expert opinion. This is arguably the least acceptable in terms of developing prior distributions, whereas base cases are the most acceptable. Subjective probabilities are subject to a lot of problems in their development, and as a result, they're not as well used as some of the other approaches. we won't really talk about subjective probabilities in this course. Entropy maximization is at the other extreme. Entropy maximization is something you use if you absolutely want to argue that your choice of prior is the optimal choice for the problem at hand. The only problem with entropy maximization is it takes a lot of work. And unfortunately, we don't have time in this class to talk about entropy maximization. But if you have a problem that requires it, that is extremely important that you justify the prior distribution that you use in your analysis, I suggest reading about entropy maximization as a way to go. From what we will talk about, you'll learn enough that you can easily acquire the skills you need if you need to use entropy maximization. Conjugate priors are an approach that it's a relatively old approach, but it is still widely used because it is very fast and very effective in developing Bayesian analyses. And that's what we'll be talking about in this video, starting in this video and the two videos that follow. Finally, non-informative priors. This would be an approach that can be taken when we really feel we don't know very much about what's going on. And this is also a popular approach. Arguably, base case or base rates, most popular, most widely used. Non-informative is probably second. And I would say that maybe conjugates and subjective would be third. And not too many people take time to do entropy maximization. Okay, so now let's look at conjugate priors. Well, what is a conjugate prior? A conjugate prior basically is derived from a problem where the posterior distribution has exactly the same distribution as the prior. So when we look at Bayes' rule, we look at the prior on the right-hand side, we look at the posterior on the left-hand side. If in a conjugate analysis, the prior distribution has whatever that is, whatever family it's from, the posterior comes from exactly the same one. So as an example, we will see this in the next video. You can have a prior which is a beta, then the posterior is also a beta when the likelihood function is a binomial. So there's a requirement on a number of things here that make conjugate analysis work. We have to have a specific family of distributions. We have to have a specific likelihood that we're using. And given those requirements, then we can develop a conjugate analysis that works for our problem. Why do we use conjugate priors? Well, it's a very convenient way to choose a prior because we're choosing from a particular family, and that family might make sense for us. The biggest reason we use it is because we can derive closed-form analytical solutions to the Bayesian problem. And this means that it can be extremely fast to compute, and it can be extremely fast to get predictions. So for this reason, the closed-form analytical solution is really a strong justification for using the approach. There's some other disadvantages, however. It clearly minimizes the importance of the data. Basically, what we're doing is we're saying, well, we've got prior data for the problem, but you know what? Let's just make sure that that data fits a particular class of distribution functions in order for this to work, as opposed to just taking the data and putting it in the way we see it. It can be very restrictive because there's only a certain number of distributions for which we can do conjugate analysis. It appears then it may be the right solution to the wrong problem. We may be getting a really good answer, but it may not be truly addressing the problem we have. To really be effective, you need to make sure you do sensitivity analysis to see how sensitive your solution is to the choice you've made to use a conjugate prior and a conjugate analysis. Okay, and in the next class, we will talk about univariate conjugate priors.